Okay. So welcome back. This morning's lecture is going to be a bit tougher conceptually than yesterday's, which was more about kind of tools and things. But it'll be leavened with one or two crude movies, and I think you'll find tomorrow's lecture rather more light-hearted. So be prepared for a bit of a tough ride for the next 6 minutes or so. But I was talking about the first of my major topics, which is what I call snapshot modeling. And then I've moved on to how to try and understand the dynamical evolution of the star cluster over more or less a Hubble time. And in outline, I'd introduce this Fokker-Planck thing, which is not necessarily the tool of choice for calculating that evolution, but it's definitely an important tool for understanding it. And I guess that's where the conceptual difficulties lie, that I want to try and clarify. Because the purpose of this is to try and understand simulations, and by the end of this lecture, you'll see what a good job we can do. Actually, very complicated simulations with binary stars and stellar evolution and all the rest of it. But you can understand the essence of what's going on the basis of these fairly simple ideas. And I said that the Fokker-Planck equation was introducing some treatment of two-body encounters beyond the smooth motion of stars in the field of the star cluster. And also appealed to your physical intuition to tell you that a steady-state solution of this would be the isothermal model, in which the distribution of energies follows the Boltzmann law. And if you turn that into a space density and solve Poisson's equation and so on, you get a space density profile which looks a bit like this. I mean, it's got a flat bit in the middle, unless you're looking at a singular isothermal. It's got a flat bit in the middle, which is the core, bounded by some core radius, and then it goes off onto an infinite halo over so, and then it's the familiar parallel r to the minus 2 density form at large radii. And if you actually look at this in projection, you'll get something which looks a bit like a star cluster with a constant density core in the middle, in projection, and then gradually decreasing numbers of stars towards the outside. And what I want to do first this morning is to explain this finding by Antonov, that if you enclose this system in an adiabatic boundary, which is a sort of standard thermodynamic trick for giving you a problem you might be able to understand, then this thing becomes unstable if the radius of that boundary is too large. I mean, out here, for example, but maybe not here. So this is the radius of the boundary, giving you a very large density contrast between the center of the isothermal and the density at the boundary itself. And you can think or visualize something like this. Now I'm painlessly going to switch to a different model for understanding the thermodynamics of this thing, which is to treat it as a gas, a model which I've already mentioned in yesterday's lecture, in which the density here is very high and the density at the periphery is very low. But nevertheless, it's a gas to the extent that it can conduct thermal energy. Now, in a star gas, this is done by means of two-body encounters. But just think of an ordinary gas, if you like the gas, well, it's not ordinary gas, but a gas in a star or something like that, just to understand the energetics of what's going on. Now, an isothermal model is characterized by a constant density, a constant temperature gas. But to study the stability of that equilibrium, you've got to see what happens if you perturb that isothermality briefly. So suppose you increase the temperature slightly in the center of the system. And I'm sorry if my diagram is obscured from most people, including the camera talking about the lecture. And never mind, you can imagine what's going on, or stand up or something like that. Okay, so you increase the temperature of the center ever so slightly. It's a slight perturbation. And then by thermal conductivity, whatever it is, heat begins to flow from the hotter part into the cooler part. So far, so good. And the effect of this heat flow is to change the temperature in the places to which the heat flows. And if this periphery is sufficiently massive, and that happens if the boundary radius is sufficiently far away, then since the mass of our isothermal goes up more or less as the radius, you can make the radius bigger and bigger. You can make the mass of this halo, although it's very, very low density, as large as you like. And that makes its heat capacity as large as you like. And that means that if you pump a little bit of heat from the center into that periphery, the temperature rises only infinitesimally. Now what happens to the center having given up some of its heat? Well, it's very nearly self-gravitating. And there's a standard argument from the virial theory which tells you that if you do remove kinetic energy from a self-gravitating system, well, of course, it tends to collapse in itself, and it recovers even more kinetic energy doing that than the kinetic energy it lost in the first place. This is the sort of negative specific heat behavior of self-gravitating systems. So while the temperature at the outside has increased ever so slightly, I'll put the arrow up here, the tiny arrow, the temperature at the inside is increased even more. And the effect of this is that the little perturbation which we started with now becomes a bigger perturbation. More heat flows, a little bit more temperature rise in the periphery, and much more temperature rise in the core. And that gravithermal instability, I think Don Bell was probably the guy who invented that term, underpins a lot of what I'm going to say in the next few lectures. And what I've just been saying is summarized in the various lines of this thing here. And the point I want to make is that this instability in a situation like this leads to core collapse, because I've said that it tends to collapse in itself, and that increase in the density of the core is something which can't be stopped by the processes that I've talked about so far. And that's why it's sometimes referred to as a gravithermal catastrophe and not just an instability. By the way, you may be worried about the presence of this adiabatic boundary here. What's an adiabatic boundary got to do with star clusters? Well, the fact is that you need the adiabatic boundary to do the computation which Antonov did. But to understand the dynamical mechanism which Lyndon Bell elucidated, the boundary actually. And in fact, if you took this boundary infinitely far away, you still get the same physical argument, and you still deduce that this thing is gravithermally unstable. Now for the first leveling simulation, what I'm going to show you is a rather crude simulation. Sorry, I'm not very good at embedding my simulations slickly into my presentations, so let me just do it crudely. So what I'm going to do is to show you two simulations starting from Atomic initial conditions, which I mentioned yesterday. And these two simulations both last, these two movies both last 13 seconds. One of them is played 100 times faster than the other. So the two movies are going to show you what happens on timescales which differ by a factor of 100. First of all, I'm going to show you the short timescale evolution of a power model, just to make you feel comfortable. So here we go. That's the wrong one. It would be. So this is what you might think the evolution of the power model looks like on a timescale of a crossing time, which I'll mention again in a minute. It's the time it takes for a star typically, going at a typical speed, to cross the diameter of the star cluster. That's a nice movie of a system in dynamic equilibrium. But what happens on a time scale which is 100 times longer, you'll see in the next moving, which is this one. Now I should say that it focuses in just on the central part, mainly the core actually of the original plumber model, and you'll see stars whizzing by. In fact, you can't see the orbital motions of the stars anymore. But if you just wait patiently and kind of blur your eyes slightly, you'll see a secular change in the distribution of the density of the point. So it's almost uniform density initially because you're looking at this place inside the core radius where the densities are almost uniform. But after around about 100 times the duration of the previous simulation, and I'll show that again because you're probably going to looking out for it, you'll see that there's an accumulation of density towards the center of the simulation here, which is the gravithermal collapse or catastrophe in action, and it's mediated by these two-body encounters, and it can be understood in terms of the physical argument that Lyndon Bell presented, or by solutions of the Fokker-Planck equation, if you want. Okay, so it shows you that there's evolution on two time scales of the rapid, smooth orbital motion on the crossing time scale, and then there's a much slower so-called secular evolution, which is a result of the cumulative effect of these two-body encounters. And that's taking place on the relaxation time scale. Scott yesterday said that I had already introduced you to the notion of collisional and collisionless stellar systems. It wasn't quite true. But what he was talking about was collisionless systems in which you're only interested in the evolution on the crossing time scale, and collisional systems in which the collisions are two-body encounters, and then you're looking at phenomena taking place on a much longer relaxation time scale. So let's go back to the Fokker-Planck equation and just see where these time scales fit in everywhere. So let's imagine that there's an evolutionary time scale which we're trying to follow things on, which I'll just call capital T. And then I'll just write down here an estimate of the orders of magnitude of the terms in the Fokker-Planck equation. So this is the order of the distribution function divided by the time scale of evolution. Because this is collisions, it's the distribution function divided by the time scale of the collisions, which is the rotation time. And here I've simply estimated the sizes of these various terms here in the usual kind of way. The gradient of the potential is g times the number of stars times the individual particle mass divided by the size of the system squared. There's a gradient with respect to velocity, so there's a one-to-one velocity here, and there's a distribution function. Now, the orbital time scale is clearly r divided by v, so this thing is the reciprocal of the orbital time scale. And that orbital time scale is much shorter than the relaxation time scale, so this term is much bigger by the same ratio than this term here. Similarly, it turns out that for a system in very low equilibrium, this term here is also 1 upon the crossing time, and this term is of the same order of magnitude as this guy. So if you're an applied mathematician, you would be rubbing your hands in delight here, because here's a complicated Euclidean equation in which there are some terms which are much smaller than others, and you're tempted to throw them away and do sort of perturbation expansion, which to some extent we'll do in just a minute. But there's a basic fact which you saw illustrated in the movie, that the relaxation time scale is much bigger than the crossing time scale. I've said here by a factor of n divided by the logarithm of n, and if you think of n as being 1,000 even, this is a large factor of the order of 100, which is the ratio of the time scales of a movie. So relaxation time scale is very much longer than the crossing time scale. So here I've repeated the same estimates, except I've removed the common factor of f, and this shows you that you've got tiny crossing time here, long relaxation time here. These two terms are big. And let's imagine that we're wanting to follow phenomena on the relaxation time scale, and then this thing here is also the relaxation time, so these two terms are tiny compared to these two terms. So to zero order in our perturbation expansion, the thing we want to do is to balance these two terms, which is just the same as the time-independent collision of the Boltzmann equation, and so we know a rich suite of solutions, let's say, of that equation. But to next order, slow time, as it were, you have to introduce a time dependence into the distribution function, which I'll do by just adding this third variable t to its list of arguments, where the energy is going to be the potential plus a half v squared, but now because the distribution function is evolving slowly, so is the potential, and so is an extra time dependence which creeps in here. Therefore, when you work out the partial derivative of f with respect to t, it actually brings in two terms, one of which is the explicit dependence of the distribution function on t, and the other one of which is an implicit dependence because the potential doesn't change at the same time, on the same time scale. So this is a kind of secularized Fokker-Planck equation now, which is basically what one means by the Fokker-Planck equation in star-cluster evolutionary dynamics. Now, there's a bit of a problem here, which you instantly recognize if you try and work with this equation. This thing here, the rate of change of the potential, depends on position. And so does the collision term. Because remember I said the local relaxation time depended a lot on what the density was, and that depends on position. But these two terms, df by d and df by dt, they only depend on the energy and the angular momentum and the time. And so in fact it turns out that if you try and do a perturbation expansion of this thing carefully, you've got to do an extra step, which is to replace these space-dependent terms by the orbit averages, which you can think of as being an average over the part of phase space, the space of x and v, on which you have given values of the energy and the angular momentum. Now you can do this very formally, and it turns out to be a kind of integrability condition for your perturbation expansion, but it's usually simply presented as an obvious thing to do, and if you want to treat it like that, then by all means. So you turn this equation into this equation, which really is the secularized orbit average Fokker-Planck equation, first derived a long time ago by Kuzmin, and these direct brackets here simply mean this orbit average. Now it turns out that if you try and solve this problem of core collapse with this equation, the dependence on the angular momentum is quite weak. Not everywhere. Towards the outside of the cluster where stuff is being kind of ejected from the core, that's not the case. But for most of the places where the relaxation mechanism is most active, the dependence on the angular momentum is very weak. And so one usually does a second averaging with respect to the angular momentum. And then you get a sort of isotropic secularized Fokker-Planck equation in which one simply, assuming that the distribution function depends on the energy and the time, and this paired direct brackets here on the left and right mean that one's simply averaging over the energy hypersurface in phase space corresponding to a given energy. And it's easy to state it in those terms. By the time you've actually carried out this calculation in practice, this term here begins to take a somewhat unpleasant appearance here. But nevertheless, this is what the Fokker-Planck equation in stellar dynamics looks like. Now, maybe not surprisingly, there is this factor which I'll call capital Q here, which is the phase space volume contained within an energy hypersurface of energy E at some given time, which I'll start to call capital T now. But the reason why I'm showing you this explicitly is simply to show you that this collision term really is a kind of diffusion term. There is a gradient of this square bracket thing to the flux, which in sort of thermal diffusion would simply be this would be the gradient, or it's the one-dimensional divergence actually, of the one-dimensional flux of thermal energy. And you'll also see that this flux has two terms, one proportional to the distribution function itself, which is a kind of drift term, which you don't often see in elementary sort of thermal modeling. But this thing here is the rate of, it's the spatial derivative of F, and if you think of that as being the temperature in our usual sort of thermal modeling setting, then what we have here is the double derivative of the temperature, which is typical for diffusion thing. So this really is a diffusion, a random walk with drift, represented by these two terms. And this stuff here is basically all that's left. It's quite amazing actually, from the theory of two-body relaxation, which I outlined towards the end of yesterday. Oh yeah, the reason why I've used a capital T here is that I've scaled out the relaxation time, or the global relaxation time. Otherwise you would see a kind of code logarithm here to indicate that this really was two-body relaxation. So there it is. And if you want, I don't have any projects, so you'll be delighted to know with the proper time equation. Because the first thing you have to do would be to write the core delivery of the main task. Now, I'd also like to mention another way of handling this rather complicated equation, which is by analogy with Jeans modeling, which is simply to take velocity moments of this thing. There's a standard, I mean, this is a standard kind of approach in kinetic theory in any kind of subject, like plasma physics, for instance. And the problem is that if you take the piece velocity moment, that is, multiply by some tensorial piece product velocity, and then you average with respect to the velocity, you always, because there's a velocity in here, you always end up including the next higher moment of the velocity. And so there's always a closure problem. You hope you're going to get by with the second or the third moment of the velocities, and you finally get involved with the fourth one. And so you've got to find some closure approach to try and represent or approximate a higher moment in terms of lower moments for which you've already got the evolution equation. And there are various alternative physically motivated ways of doing this, and it was first done by Richard Larson, he of star formation fame, who applied a technique from star formation to the star cluster problem by doing this for the first time. There's an even more crude but very effective way of doing this whole thing, which is really to treat the star cluster like a star, literally. So that the first two equations here are the same as the first two equations in stellar structure and stellar evolution theory. And the differences arise where one tries to write down something like the luminosity of the star. That's why I use L here, L divided by 4 pi r squared is the luminous flux across a sphere of radius r. And so here one's got the luminosity, or the luminous flux, given in terms of the space derivative of the square of the dispersion of the velocities. So this is basically the temperature, telling you that the luminosity, the luminous flux is proportional to the temperature gradient, and this thing here tells you all about the relaxation. So it's a very, very simple formula for the thermal conductivity, if you like, and this is what was devised by Don Lyndon Bell. It had been tried by Sugimoto a few years earlier, but he used the thermal conductivity of a plasma, and that turned out to be inappropriate for stellar dynamics, slightly mysterious. And then there's this slightly mysterious looking formula here, which actually involves essentially the specific entropy of your gas. And this thing is just the first law of thermodynamics, basically, telling you that the rate of change of the thermal energy in a shell is given essentially by the difference of the luminous flux, sorry, the total luminosity across the bounding radii of the shell. I think it's also a second moment equation that's still represented in this term. So this constant C here is a constant, this thing C here is a constant which one can't determine on fundamental grounds, but you can determine it empirically. and everything else is defined down here. Now that gas model has been very, very important in trying to understand things like gravithermal catastrophe and core collapse. And this is where Lindenfeld teamed up with Peter Egerton, who knew how to solve the equations. And they produced this famous profile for the density profile in a collapsing core. And they actually found a self-similar solution of the equations which I've just written down. And self-similar solutions in a log-log plot of density against radius simply means that the evolution is steady translation of this one profile towards higher central densities and smaller core radii. And in fact, if you do a numerical integration of the isoptimized copper Planck equation, that's exactly what you see. Here's the initial density profile of the Plummer model, and then central density just inexorably gets larger and larger. The radius of that central core becomes smaller and smaller, and this gas model solution of Lindenfeld and Egerton is a famous kind of encapsulation of this rather complicated. It's a very remarkable fact, actually, that self-similar solutions, which is what we said is a homological solution of the problem, turn out to be so important in understanding numerically evolved solutions. And we'll see this time and time again. And if you're interested in, I mean, it's something which you don't often get in textbooks. Why are self-similar solutions important? But it's one of the things I learned from Donald Lindenfeld just by talking to him. You can find some nice paragraphs in these two papers by Donald, which will explain to you their essential role in complicated nonlinear problems like this. For an applied mathematician, this is an example of finite time blow-up because the central density does go to infinity in finite time. And that's a common kind of phenomenon in nonlinear thermal diffusion as well. What do you call them? Reaction diffusion equation.
This is isothermal? It's rho is like 1 over r squared?
It's actually r to the minus 2.208. And we talk about isothermal. This is hotter than this is cooler. The other thing I want to mention, thanks for holding up about this, is that the amount of mass involved here becomes smaller and smaller. So this core gets denser and the radius gets smaller fast enough, the amount of mass involved becomes tiny. And that's its salvation, basically.
Douglas?
Yeah.
To what extent this depends on the conduction or diffusion coefficients? With similar type of similarity solution, it's also been suggested in the star formation.
Oh, yeah.
And by Shu 77.
Right.
And it also has this nearly r to the minus 2 profile. And I think
well, that has exactly minus.
Well, yes. At a slightly earlier stage, we try to do things with Bernard Carr, with GR, and try to look at the growth of cosmological black holes. And also got an r equals to minus 2. But there's no diffusion in that particular system. It's just the expansion of the rare refraction rate.
Yeah. I think this has been examined. There was a paper written by Pete Hutton, a student, probably about 20 years ago now, which I don't think ever got published. It actually went into this, what happens if you tweak the various powers of the density and the velocity dispersion or the temperature in the thermal conductivity coefficient. And I mean, there's just a domain in which this happens. Basically, I think you've got to ensure that the heat doesn't flow out of the, oops, sorry. Yeah, you've got to make sure that the heat doesn't flow out of the low density stuff too fast. I think that's the essential point. It's got to flow very well around the core, but not too long.
Yeah, there in both of these other contexts, it's not the heat transfer that did it.
Okay.
I think it's the expansion of the rare refraction rate.
Oh.
Because once it there's a singularity in the middle.
Okay.
So once it goes in, there's a pressure wave that goes out.
Okay.
And it's expansion there that gives rise to
Oh, but it's after this phase he's talking about. It's after it reaches infinity.
that's probably true.
Okay.
Yeah,
So
that's,
beforehand it's already.
I agree. Okay.
Yeah.
It's after the
Unfortunately, the star cluster finds some other way to do
Yes.
it.
Thank you.
Okay.
Now, all that I've been saying so far this morning has been about one component systems, stars all the same mass. So let's just have a look at what happens in this process. If you have two components and the individual masses are M1 and M2, now imagine that M2 is bigger than M1. So one can imagine on physical grounds or in the theory of relaxation that you tend to approach, the collisions make you tend to approach equipartition of inequality of temperatures. And if you start with equal velocity dispersions, which theories tend to do, then this term here is initially much bigger than this term, and therefore the effect of the collisions is to try and reduce sigma 2 squared, which is the velocity dispersion of the heavy stars. So that the species 2 tends to lose kinetic energy and sinks in the potential well, and that gives rise to a spatial segregation of the two species, the heavy stars sinking more rapidly to the center. And you can do two-component Fokker-Planck simulations, which was done a long time ago by Heggie and his then-time student. And typically what happens is here. You can think of this as being a time axis. It's actually a central potential axis. This is the logarithm of the density. And the density of the heavier species goes up faster than the density of the lighter species, although this density still does increase. And you'll observe here what happens to the approach to equipartition. I think I'm not quite sure why I think the match ratio here must be 10 to 1 actually, because the ratio of the temperatures, no, the ratio of temperatures is not 10 to 1, it's more like 0.5 to 0.25, so 2 to 1. But the heavier species is hotter initially and tends to cool down, which of course is what drives the mass segregation. Meanwhile, it's giving up its thermal energy to the low mass component, which is tending to heat up. But you don't approach a situation in which these two curves coincide. You always remain in thermal imbalance from each other. And of course what happens is that, it's like I said with regard to thermal catastrophe, although the second species tends to collapse in on itself, in doing so it's a bit self-gravitating and actually its thermal energy tends to increase again, and it simply keeps running away in advance of the rising center temperature of the light star. Now, whether this happens or whether you do actually have coincidence of these two things depends very much on the total masses of these two components, and that was elucidated by Lyman Spitzer previously actually in the so-called Spitzer or mass segregation instability. It turns out that if the total mass in the heavier species is too large, then the heavier species runs away from the lighter species, and the two species can never reach actually equipartition of velocities. So one can't automatically assume that equipartition of velocities is achieved in this rush towards core collapse, and in any event, this process does not stop the actual collapse to density, even if the two components from the thermal. So one has to ask the question then, what does stop the collapse? Because there's a scientific theory which predicts an infinity, and here we've got infinite density in finite time. There must be something wrong with the theory. And what's wrong with the theory is that it relies on two-body encounters. And actually, of course, stars are interacting with more than one other partner at a time. And in particular, the high central density at the end of the core collapse gives you a clue to what might happen. We'll come to that in a minute, but because the density is very, very high, then a star is crowded by neighbors, and particular C-body encounters can become competitive. And here's an example of a C-body encounter. 3 stars, one here coming in from the top right, one coming in from the bottom left, one coming in from the bottom right, and there's a miraculous C-body encounter here which gives energy to this incoming star here, which then these seen, and these 2 stars become bound by having yielded up that energy to these 2 stars, and these go off in a more or less permanently bound pair. And this kind of C-body interaction isn't taken into account in the gas model so far, or the proper plant model so far, and it may be the salvation of core clouds. Now, again, I'm going to try and appeal to your physical intuition to try and understand with one equation what happens in encounters between a binary and a single star. So here's the binary, and here's the approaching single star. And the way to analyze this kind of thing is in terms of so-called Jacobi coordinates. And the derivatives of these Jacobi coordinates are the velocity of the incoming star relative to the barycenter of the binary, and the relative velocity of the 2 components of the binary. And if you write down the total energy in the barycentric frame of this C-body problem, then it splits up into plainly into 2 pieces, one of which is simply the energy of the binary, and the other one of which is the energy of another quasi-binary consisting of this star and this barycenter. And this is, I should have said, put some twiddles equals here, because this is neglecting the fact that this is not our point mass as seen by the third particle. So this is very good as long as they're far away. But as this third body comes in towards the binary, as long as it interacts vigorously enough, I'm simply going to appeal to your intuition to argue that if the incoming velocity is much bigger than the relative velocity of the 2 stars in the binary, then there's a tendency again towards equipartition, this time between different degrees of freedom, in which some of this high kinetic energy here will be imparted to the binary. And if that happens, the binary increases its kinetic energy without much change in the potential energy. It tends to become more unbound. And the opposite happens if this incoming speed is very, very small. Then the binary is like a rapidly rotating dumbbell approaching with this slowly approaching third star, and tends to impart some of its kinetic energy to the third star, which then shoots off with high speed. So that's what's summarized by these statements here. The incoming speed is very big, and the binary tends to get kinetic energy, which means that it's tending to be disrupted, and the other thing happens if the incoming star is moving very, very slowly. And then it's convenient to simply observe that the relative speed of binaries can be written in terms of the semi-major axis of the binary, and then one gets a condition not involving little v, but involving the semi-major axis, and this sigma squared here, which I've previously used for the velocity dispersion of stars in the system, which we can take as a proxy for this capital V here. If this stellar velocity dispersion is small compared with the energy of the binary, then the binding energy of the binary tends to increase because its kinetic energy is decreased in this encounter. Obviously, it's more complicated than that. We'll see how complicated in just a minute. But the basic story, certainly for equal masses, is about right. And this distinction between whether our binding energy of a binary per unit mass is bigger than or less than the velocity dispersion, that distinction is rather critical. And so binaries in which this is true are called very hard binaries. Binaries in which this is very much less than the equal period are called very soft. And it's the hard binaries which get more and more energetic, and in doing so pump more and more energy into the translational motion of the single stars, and indeed at the very center of the binaries. That process is a kind of exothermic process which actually stops core collapse. Now, a long time ago, Lyman Spitzer, I think it was, estimated the timescale for the formation of a hard binary, and he found that it was proportional to the relaxation time, but very much longer even than that. Now, the core collapse is taking place on the relaxation time, so it looks as though this timescale for the formation of binaries is too slow to actually help you. But you see what's happening in the core. If you just look at conditions in the core, the number of particles in the core is decreasing. And that's going to zero as the central density increases to infinity. I mentioned that fact a few minutes ago. And therefore, it turns out that the timescale for the formation of binaries actually becomes competitive with the timescale for two-body encounters, which are driving the core collapse. And so the three-body binary formation is actually what can save you. And it's saved you because it's exothermic. So, this is a heating mechanism which prevents or stops at some point. It stops core collapse and actually reverses it. Now, the one sort of interesting extra twist to this tale which has been added in recent years was a paper by Atara Tanakawa and these two guys. And they pointed out that actually the formation of binaries usually involves more than 3 particles. And post hoc we realized why this was the case, and certainly 4-body mechanisms are important, which is something which was missed while this subject was being developed over previous decades. And I think I'd better, oh yes, I've got a numerical example, so let me just bring on the ice creams again and show you a look. And so what I'm going to show you is a scattering event, rather like I described here, in which there's this innocent binary going along and then a third star comes along and interacts with it. So here's the third star coming along, binary fizzing around and around. So instead of actually leaving the scene completely, this guy's just gone off to the frame, and he comes back again, and another interaction. And so this repeats for a long, long time. Partial rejections of the, excuse the slight glitches, these are just in the calculations involving the actual model. Now I'm showing you this for 2 reasons. One is to show you how complicated interactions actually are. It's not nearly as simple as I was trying to say in terms of direct partition of kinetic energies. As the eye of experience, you can see that we're getting near the end here. And here it comes. And that's the end of the simulation. Long, long lapse. Now, the reason I showed you that was twofold. First of all, as I said, to show you that things really are quite complicated in these three-body interactions. And the second thing was to show you how long that interaction lasted. And it's for that reason that four-body interactions actually are important. At least that's the reason that we understand. Because while this is going on, this is all taking place in a very, very dense core where at least there are a dozen other stars. And the chances that one of these stars will interact with the three-body system while it's trying to sort itself out are very high. And so four-body interactions are actually also a competitive case. Okay, back to the hard work. Four-body mechanisms are important. So now what I'm going to try and do is to, this is just a little bit of a fresh start. I'm going to try and introduce you to two solutions of this rather complicated looking equation, which pieced together give you a kind of global view of the dynamical evolution of a star cluster. So these two solutions, which I'm going to talk about, were derived a long time ago by Michel. And you don't need to read French, although it's very, very nice in these papers, because from Menon is here, we translated these and put them on National PH a few years ago, and so you can read it in very simply. But, yeah. So, yeah, and these two papers are very well worth reading. They're very contrasting. This thing's about 50 pages long, this is about 5 pages long. But these two solutions, which Menon arrived at here, I think the underpin, well, certainly my understanding of long-term evolution of these things. Now, the first paper was one which dealt with a so-called tidally truncated cluster that's bathed in an external tidal field like I described yesterday. The tide is described as a cutoff, so the cluster has an absorbing boundary at the tidal radius RT. And actually, I'm not going to go through the calculation in detail, but you should understand that this means that if the cluster is embedded at a certain point in a galaxy, then evolution truncated by this tidal radius corresponds to evolution of the cluster at constant density, mass times number of particles, which decreases with time, divided by the cube of the tidal radius, which also decreases. Now, Michel was, I'm amazed every time I see what he went through to get to these solutions. He observed that deep down in them, the only thing which is happening is collisions, and these two terms here are very, very small by comparison with the collision term, or just bits of the collision term. And therefore, deep down in the system, at the inner boundary conditions of this solution, as it were, you just have to write down a solution in which the collision term is zero. Now, I told you what such a solution might be, which is the Boltzmann distribution, but somehow or other, Michel realized that that wasn't quite enough. In fact, it's not enough because this is equilibrium. And so one has to go a little bit beyond that. And so he said, well, let's try and do an expansion of the solutions of this thing. And he showed that, in fact, you could do that, and there were a couple of additional terms, which for E very, very large and negative are small compared with the Boltzmann piece. And he also showed what these two terms actually correspond to. This corresponds, the first term here corresponds to a certain flux of energy out of the center of the model, and the second one, this K2 term here, corresponds to a flux of mass. Now, even Michel wasn't prepared to contemplate a flux of mass out of the origin into his solution, but he was prepared to tolerate a flux of energy, because he already knew some old N-body simulations by Sebastian von Hermer, which exhibited this process of binary formation and binary exothermics. So he was imagining that there was some kind of central object which would emit energy, and so he was perfectly prepared to admit this in the central conditions of his model. So then the problem which he had to solve was this one. This is actually an integrated form of the orbit average isotropic Planck equation, which I've already shown you. Because there's no d by dE out of this collision term here, it's an integrated form. It's actually equivalent to a fourth order system, and then these are the inner boundary conditions and three similar expressions. The outer boundary conditions are just telling you that the distribution function goes to zero at the tidal radius, where you've got this absorbing boundary. This looks like a very, very weird boundary condition because it's trivially true at the energy equals zero. But when you try and solve this equation, this kind of formulation is appropriate. Now that's a rather savage nonlinear equation, and so Henon approached this by a kind of iterative method. At least I thought that this word Platonic, which he uses in his paper, meant iteration, but in fact it means groping around in the dark. Now, it's the kind of thing that one does when one tries to solve a nonlinear problem for the first time. You try things out and see, oh, well, this should be a little bit bigger, let's try that, and so on. So, after 6 hours of computing on an old IBM, something or other, again, a solution. I've had a number of students working on this in the last few years because we would like to try and do the same thing for two-component systems, and we more or less get to similar kinds of results to Michel's. I mean, it also took us about 6 hours, but we were able to examine the dependence on integration parameters and tolerances and so on in much more detail than I guess he did. And I'm pretty convinced about all four digits in these numbers, but it doesn't really matter for a lot of problems. Now here's what his solution actually looked like. Here's the distribution function. This is a log. This is a log of f against energy. So this piece straight here is very nearly Boltzmann, but then it comes crashing down towards the tidal boundary. The density does something similar, although it goes off to infinity at the center. And here's the radius as a function of the potential. And the important thing is the time dependence. And this is the thing which underpins our understanding of what happens to star clusters in tidally bound domains. The radius goes to 0 at a certain time. I've said here TR is 0, but this is simply a time scale which is proportional to the initial relaxation time. The mass goes to 0 at the same time because stars escape over the tidal boundary, and the relaxation time decreases linearly with time. And, the behavior of the relaxation time will be important. So this thing here is not the relaxation time, but it's a measure of the relaxation time initially. And this is a self-similar model, model analogique, as Michel said. And then in his later paper, well, the first paper was 50 pages, this is 5 pages, and he simply states the answer for what happens in an isolated model. He didn't even state how he solves the problem, and so it took us a long time to figure out how to do that, and we tried to repeat this solution. So here in summary are the two solutions. This for an isolated cluster, the radius expands as the 2/3 power of time for large times. The mass stays constant, there's no mass loss mysteriously in this problem. But it's not so mysterious that it's great fun to try and understand actually what the mass loss is in an isolated system, and we'll have an opportunity to speak about that in future weeks. Relaxation time increases linearly with time, and then I've already shown you the dependence of the radius of the cluster, its length scale of the cluster, its mass, and the relaxation time in terms of time. And basically, this summarizes the entire life cycle of a star cluster, except for the process of core collapse, which we already kind of understand from the Linden-Bell and Eggleton thing. So from Linden-Bell and Eggleton, there's core collapse, and that forms a very, very tight core, which can give out energy like Michel Hénon assumed. And if the star cluster is tiny compared with its tidal radius, like a newly born, very, very massive star cluster, it behaves more or less like this isolated model. The tidal radius is so far away. And then the cluster expands, just like this formula here states, and so the cluster becomes bigger and bigger, and eventually it does make contact with its tidal radius. Stars do begin to escape over this absorbing boundary, and then the rest of the lifetime of the star cluster is described by the tidally truncating model. And that's Hénon. And that's Linden-Bell. So I think from these 3 papers you can more or less understand everything about the long-term dynamic resolution of star clusters. And remember, although this is conceptually hard, this lecture, what I'm trying to do is to give you the background to make it easy to see what's going on in very, very complicated simulation. And I'm going to start that process in a minute. Just to think of how I remember what I'm up to. Oh yeah. Here's a piece of work by Mark, which he taught me this when he came to Edinburgh for a few months a few years ago. So although he allowed me to be on the paper, I mean, all I did was to teach him about Eon and stuff like that, and it was basically his idea. So let's make this assumption that the initial radius of a star cluster is very much less than its tidal radius, and assume that the cluster expands like Enon's isolated model. Some of the mass begins to meet the tidal radius, and then after that the thing will evolve rather like Michel's tidally truncated model. Now, there's no way of joining these models smoothly, rigorously, but one can do it in an ad hoc manner, as long as it's done judiciously. And typically what happens then if one does this is that the evolution of the half-mass radius of a star cluster begins by expanding like t to the 2/3, but then as it approaches the decreasing tidal radius, which is like here somewhere, it starts to decrease again and then decreases as time approaches a certain origin with the one-third power. So that is, to some extent, the entire life history of a star cluster, except that we don't worry about what happens in the little core collapse phase, which is a very, very fast early phase at the very, very beginning. And Mark's tremendous observation was to use Michel's results for the isolated model. Let's go back a couple of frames just to remind ourselves about that, in which the relaxation time is given by the initial value in some sense plus the time itself. So if that initial relaxation time was very, very small, and that's true if the initial cluster was very, very complex,